Welcome to lecture number 2 of module 2, that is equipment and stability constraints in the power system. In lecture 1 we saw that the per unit system and also the various constraints related to the equipment and the system. Here now we are going to discuss the various equipments. Those are very important in the power system, and the first one is the generation. Already we know this power system that we have the synchronous alternators, and as I said, the alternators, because they produce the alternating currents, or you can say sometimes very conveniently said the AC current, are used, and these alternators are basically run by the turbines, and the turbine is basically rotated with the different mechanism, whether it is due to the steam or through the hydro or through the gas, and then based on that we say the steam turbine, hydro turbine or your gas turbine. There is a different type of synchronous alternators. One is a cylindrical, another is your salient type. In the cylindrical, it is normally number of poles are limited. However, in the salient, the poles are more and the poles are at the salient in nature. High-speed synchronous generators are used in thermal power stations, or you can say steam turbines. Where the steam turbines are used, we go for the high-speed alternators, because the efficiency of the steam turbine is high at the high speed, whereas it is reverse in the hydro turbines. The performance is better at the low speed. So the steam turbines, that is here, gives better performance in terms of efficiency and in terms of operation, and then we run at the high speed, whereas the efficiency of hydro turbines is larger at the low speed, and therefore low speed alternators are used. Now how much high? You know, this we have the 50 Hertz supply system, and the number of poles in any power system, any alternator cannot be this odd number. It should be the even number, means the number of poles will be 2, 4, 6, 8 and so on and so forth, and then this speed is related by the system frequency and the number of poles, and it will be used and it can be given with the equation n, that is the speed in RPM will be equal to 120 multiplied by the system frequency divided by number of poles. So the number of that is the number of pole in the minimum number of pole cannot be less than here 2, and if your system is operating at the 50 Hertz, then your n will be your 3000 RPM. However, in the USA, Canada and Mexico, which is operating on the 60 Hertz system, then this will be your 3600 RPM. So the maximum speed that we can achieve in any alternator is your 3000 for the 50 Hertz cycle system, and it is 3600 for the 60 Hertz cycle system. Since in India it is a 50 Hertz supply, even though it is not in India, it is in Asian country as well as the European country, the system supply frequency is the 50 Hertz. So the maximum speed of any alternator will be your 3000 RPM. And it is related with this equation that the speed in RPM, it will be 120 F divided by P. P is the number of poles, F is the frequency, and 120 is a constant, that is a multiplier. So that's why here, as I said, this thermal, or you can say steam turbines, are more efficient. So they should have higher efficiency, and for higher efficiency we have to go for the higher speed. So if it is a higher speed, then we have to construct our alternator in a such a way that it should not feel high centrifugal force. Otherwise what will happen? There will be possibility that the poles which on the rotor, it may go out, and that may damage your alternator. So as I said, the poles cannot be even number, it will be always it cannot be odd number, it will be always even number, means the pole number of poles, it will be 2, 4, 6, means it is a factor of 2. The highest speed, as I said, it is 3000 for the 50 Hertz cycle system, and for the 60 Hertz it is a 3600 RPM. With 2 number of poles, the cylindrical construction also called as a wound rotor or sometimes called round rotor, is advantageous in terms of cost and the performance. Field winding, which requires a relatively small power, it is normally 0.2 to 3% of the machine rating, is placed at the rotor, and the armature binding, which is designed for generation of the balanced three-phase voltage, is on the stator. Means the rotor where we put the field. Now you can assume that you have seen the DC machines. Normally field is on stator and the rotor we have the rotor winding. But here it is a different, means your rotor is on, your field winding is, or sometimes it's called field winding, it is on your rotor, where the armature is on your stator winding. As the speed of turbo alternator is high, the diameter of machine is kept minimum. As I said, why? Because we want that the minimum centrifugal force should be applied, and therefore we can have the stable machine operation. To keep the same electrical loading, you know the proportional of area multiplied by length, the length of turbo alternator is increased. And whereas Salient type of rotor, which is used in the hydro, the length is minimum but diameter is more. So you will find that in thermal power stations, the length of machine is very large but the diameter is less. However, it is a reverse. In the hydro, it is the diameter is very high whereas the length is less, because here the electrical loading is proportional to the area as length. So to make the electrical loading same, if you want to go for the minimum dia, means area is less, length must be increased. So in the turbo alternator, the length is very high and diameter is kept as minimum as possible. However, in this hydro, normally we use the Salient because we go for the large number of poles and also they operate at the less speed. So it is convenient to use the Salient type, and therefore for the Salient type we can have a large number of poles on the rotor so that the diameter of this machine is increased. So of same electrical loading, if diameter is increased, we can have a smaller length of this. Also this thermal power alternators, normally it is horizontal, it is rotating. However, in the Salient, and that is used in the hydropower station, it is a vertically. Water is coming and that is the turbine is rotating and your alternator is connected with this turbine. To minimize the current flow in armature, which reduces the copper loss, the voltage raising of the alternator is increased, but it is also limited due to the cost and the insulation loss of the material. As I said, if you want to go for higher power, and suppose you can see you have a machine that is your 100 MVA and your voltage is, let's suppose, 10 kV, then current will be, if you are talking here is a three phase, so then phase current will be your 100 divided by under root 3 10 kV. Here it is MVA, so it will be 10 to the power 3 ampere, or I can cut out this, so it is kilo ampere. So you can see this much kilo ampere current is flowing. Now if you want to increase this voltage to 100 kV, what happens? This current is reduced, and once current is reduced, we know this I square R loss, that is loss, the real power loss, and this loss basically generate heats in the winding. So what we normally go for, we try to increase the voltage to reduce the losses in the system. But there are two problems with the increasing the voltage. If you are going for the increasing voltage, you know any alternator, here this is your armature where the different bindings are here at the stator, and we have here rotor that is rotating. So this, if binding is operating at 100 kV and this outside cell it's a ground potential, then we have to go for the insulation level to provide for this higher voltage. Then we have to use the insulating material that can sustain this high voltage level. So to design it, it is very expensive to go for this such a high insulating material. So what it is a limited. We cannot go for keep on increasing the generating voltage. So that's why we have a limitation here, that is a constraints of this generating that's equipment, that is a generator, that we cannot increase the voltage as much as possible. Means we can go up to the certain level where we can see that we have our dielectric material that can sustain that voltage, so that there should not be any short circuit, there should not be any fault. That is what is happening if this is your binding conductor and this is your zero potential where your conductor is there. If the insulating material here, this is a short circuited, this is just like a line to ground fault. So this is a fault and that must be protected. And so that we have to put insulating material here in a such a way that it can sustain that voltage level. So the maximum voltage level that is available in the world, it is not more than 33 kV. Main problem here that we cannot increase the voltage excessively than more than this, because at this counter, at the corner here you can see there will be more field. This stress, the dielectric here, this E field will be higher at the corner. If there is any sharp corner, there will be more. So there will be possibility of hot spot and also more eddy current and more losses here, and there will be some problem here. So far throughout the world we have the generators rated, the voltage rating is up to 33 kV. However, in India the maximum voltage rating of alternators are 21 kV, and these alternators are rated at the 500 megawatt. We have the alternators at Singrauli, Rihand and Para, they are basically at the 500 megawatt units. Is not a unit means at any power plant station there may be possibility that we have the several units, and so it is a one unit is rated at the 500 megawatt. The voltage rating of other Indian generators units are 11 kV for the 50, 110, 100 and 15.65 kV, sometimes it is also called 16 kV for the 200 and 210 megawatt unit. So we have the two type of alternators. One is your window rotor and other is your salient pole. For salient pole, as I said, we use these type of alternators in hydro, but for the thermal or you can say steam turbines where they are rotating the alternators, we use window rotor. Now the phasor diagram to know this other capability. So just these are the various voltage ratings. So we have seen that the constraints of the generating stations or generating units are limited by the voltage due to the dielectric or you can say insulation limit of that. So we will see other constraints of, and we can say that is a capability of the generators. So if you will see the capability and the constraints, what is the difference between the capability and the constraints of generators? Basically there are various constraints, those limits the capability of the generator. So the capability is a curve that is bounded by the regions of the various constraints. So we will see the capability curve of generators in terms of real and reactive power later, and again that is depends upon the heating limits. We have seen the another constraints and the you can say limiting value of the alternator is the voltage due to the dielectric and due to the design limits. So the various limits are imposed on any elements. It may be your thermal limit, as you can say heating limit, and another one is your dielectric due to the dielectric constraints. Now this alternator basically it is called the doubly excited, means we have the field binding and we give the DC field to this rotor, and we have the armature where is the AC is going to be produced. So we have your the field MMF, and another we have your armature MMF, means we have the MMF at the rotor that is called F, and we have F that is of the armature. The resultant, if you will see that here we have the armature currents, and this resultant of this armature, because we have three phase windings and they are displaced by 120 degree in space, so that you can see the resultant here Ft will be also rotating in the air gap. This flux, that is MMF, will be rotating at the same speed of the operating frequency, that is omega 2 pi f. So then we can have this f is rotating at the synchronous speed. This ft is also rotating at, and this is due to your fa, it is rotating with the same speed. Then we can add these two MMF. Here you can see this value ff minus fa. Basically this is your called the armature reaction. It's try to oppose. So your resultant MMF will be Fr, that will be FF minus here Fa. Here you can say this Fa is added here. So this resultant will produce your resultant voltage. Now we can see that this F will give your voltage induced, that is EF, and this we know it very well, this induced EMF E, that is produced by the field, and we have ER. So these two are related by another here, that is your XA multiplied by IA, and this is here you can say current, it is a perpendicular to here, means it is a 90 degree. So what is happening, that this we have a reactance here XA, and we have the reactance, that is a leakage reactance of this winding in the generator. So we can write the expression, and this equivalent, if you can say this X that is called the synchronous reactance, is your addition of XL plus your XA, and this XA is due to the armature reaction. So this total X is basically the reactance that is seen by generator, that is experienced by generator. So now you can say, we can write the equation here, your terminal voltage of the generator will be, or in other words we can write here your EF will be your VT plus your IARA plus here JIA into XS, and here all these are the phasor quantities. Now this terminal voltage, that is the voltage of your alternator, which can be seen here, this is your terminal voltage of alternator. So the reactances and EF, just we have written, this is your equivalent diagram of an alternator. Now this whole rotating mass can be represented by this equivalent electrical circuit, where this E is the field EMF, that is again depends upon the field excitation level, this voltage. Then this current IA, that is your armature current, and it is flowing through the binding resistance, and this XS has two components. One is the leakage, this actual inductance of the coil, and due to this armature reaction component, so it is called synchronous reactance. And this is your terminal voltage, and then we have, let's suppose, one load, and load it may be here the transmission lines, those are carrying power. So to minimize the current flow in the armature, which reduces the copper loss, the voltage rating of alternator is increased, but also limited due to the cost and the insulation cost of the material. So this voltage, as I said, is limited due to the cost. We are having the insulators, those can sustain high voltage as well, but still it will be very expensive. So always we engineers try to design a system that will be the techno-economic analysis, we can say. So the cost should be minimum and the performance should be better. Now let us see again, this is the equivalent circuit of the cylindrical rotor type of alternator, synchronous generator. We can write this, the three-phase complex power S at the generator terminal here. It will be the terminal voltage this. Here I have represented at the single phase. So this current conjugate means 3 times the voltage, this is a phase voltage, multiplied by current which is flowing here, and that is a conjugate of this. So we can write this current IA, armature current here, this voltage minus this voltage divided by the impedance. So we have written here EF, here we have written here the delta. Taking this voltage as a reference here, we have seen that this EF is having some angle delta. Now you should be very much careful and you should know what is this delta. This delta is known as your torque angle or sometimes power angle, because this is the angle between the two voltages. Means it is a terminal voltage and this is your field voltage. So this is called load angle, and it is different than your power factor angle or insulation angles. So this angle, as we know, the power factor angle is nothing but the angle between voltage and current. However, this load angle is between the two quantities of the same unit, means this voltage, current and current. So this is delta, that is with reference to this voltage 0. If you are taking here, let's suppose 15 degree of this voltage, then here this will be your delta plus 15. So this is basically, I can say, with the reference to this terminal voltage, this angle delta, that is the power angle. So we can write the current which is flowing, this voltage, that is voltage EF angle delta, minus this voltage divided by the impedance here, which I have written here. If you will put this value here and you will take real and imaginary components separately, then we can see the real power at this terminal here P will be nothing but 3 times EF Vt upon Zs cos beta minus delta. Here the beta is the angle of here, means the angle, if you say this is your R, this is your XS, this R, so this angle is your beta. So this is called also impedance angle. So the real power can be related at this one, is this expression, and the reactive power can be denoted at this one. We know that this access is very high compared to the resistance of the winding, because normally we use the very pure conductor. Conductor means we use aluminum or copper. Normally we use the copper in machine binding, so the resistance is very less. So what we can do, we can see here this Zs we can simply write is a Zx, or we can write here X angle 90. So putting this beta is 90 degree, and here Zs is your Xs, or here what the value, and then we can get the simplified expression here that the P will be your 3 times E of Vt upon Xs sin delta, and the reactive power we can get this 3 times Vt upon Xs E of in bracket E of multiplied by cos delta minus Vt. Here you must always know that here EF and Vt, they are the per phase quantities, they are not the line to line. So the per phase here, this is also per phase, and this we are getting the 3 phase, because here 3 is coming. So from here you can see, if you draw the angle between the P and the graph between the delta and P, we will get this diagram, and this is called power angle curve. Means here this is the variation of delta here, and here the P, we are getting this sinusoidal curve. Now this maximum value here which we are getting here, it is nothing but your 3 EF Vt divided by Xs, and this value is called the stability limit, state stability limit, or static limit. So this is another limit on this generator, means this generator cannot produce power in steady state more than this value, because the maximum value here for the sin delta will be unity, and this unity will be only at this delta is equal to pi by 2. From this diagram we have the two sides, another this side you can say, this is one side of this delta by pi by 2, and this side. Now you can say for any value of P here, let's suppose any value I can say P naught, if you draw this here line, means this intersection here as well as here we are getting, means we are getting for the power which is this generator is delivering, we are getting delta is this, another delta is here, means it is I can say delta 1 and delta 2. Now the question arises, at which angle this machine will operate. This operation here, this angle is smaller, this angle is larger. We can see that this area, this side is called unstable zone. So we cannot operate the generators in this zone, means always our angle should be less than pi by 2, and this sided area, it is your stable zone of the system. Now how we can say that this is stable or unstable? Let's suppose our system is operating at point A. If there is a sudden increase in the power, if some power is increased, what happens from this expression? If the power is increased, keeping this constant, we have to go for this reduction here in the delta. If you are increasing this sign delta, means here beyond this angle, what will happen? This power, if your angle is increased, what happens? You are coming here and again your power is reduced. But we want more power. So this area is unstable and this area is stable. You can see from this area, this is, let's suppose, your A1, and if there is a further power is increased, then you are here and your delta is increased. No problem. But here your delta is increasing, but your power is reducing. So it is a reverse. And that's why this zone is called unstable and this is stable. So we must operate our power system in this zone, that is a stable zone, and it is one of the constraints of the power system generator, where this is your steady state constraints. It's not a dynamic. And this is related to your power flow here. Now we can see in the reactive power here, as you know, the reactive power is also one of the very important component of this generator which it is going to generate, and that is related by this expression, that is E of cos delta minus Vt. So this value will be positive if this here is more than this Vt. This may be negative because here Vt is the magnitude, positive always, x is always positive. So only the sign depends upon here. However, this power is every time is positive because that angle always start from 0 to delta, that is delta here, and it is a pi by 2. So it depends on whether this Q is negative or positive, and it also known that whether it is overexcited or underexcited. So in this expression, that is the real power, that is the P that I said, it is your, now I can write this real power P in terms of the P max sine delta. This delta is basically the difference of the voltage angles of the two buses. Means here, for example, just I represented your this system. Here, this is your EF and this is your VT. So it is a voltage difference, voltage angle difference between these 2 points. Means here, if you are going to use like your EF, I said it is your angle delta, and your terminal voltage was 0. So this is the difference between these two angles. If it is not a reference value, so this delta is the angle difference between these two voltages. Means if this is, let's suppose, lambda 2, this is your lambda 1, so this delta will be nothing but your delta 2 minus delta 1. So this is the voltage angle. Now again, you must be very careful, and this delta is your load angle. However, this angle delta 2 and delta 1 are the voltage angles. Both are totally different. So the difference of the voltage angles is your load angle between two adjacent buses. If a system or element is connected between two buses, then it is the difference of their voltage angles is your load angle. Now let us see the reactive power, which is related with your the terminal voltage, excitation voltage, and here this axis. It is basically, this expression is only valid for your cylindrical rotor generator or motor. It is equally valid for motor as well as the generator, means it is for the cylindrical machine, I can say. So the generator delivers reactive power to the system when it is more. If you remember here in the previous, it is your terminal voltage and it is giving to the load. So this is your nothing but your R, this is your XS, and this is your alternator which is giving feeding power. So we calculated here this P and your Q. So this P and Q is the injection of real and reactive power at the terminal buses. So here P is every time positive since it is a generator, and this generator received power from the turbine in terms of mechanical power, and then it is converted to the electrical power through this alternator, and finally it is flowing to this bus, and then it is no doubt it is your system. So from the previous equation we saw here this value is positive if this value E of cos delta minus Vt is positive, otherwise it is negative. So I can say this machine will delivers reactive power or injects the reactive power when E of cos delta is more than Vt. And this condition is said to be overexcited mode of operation of the synchronous generator. Means it is overexcited, means this value EF is more than is your terminal voltage, it is called your overexcited. The reverse is underexcited, where this EF cos delta is less than your terminal voltage, and in this case this generator absorbs the reactive power from the system, and now especially the absorption of the reactive power by the alternator is normal case, it is not allowed unless until there is some specific need. So we can see one very good relation that we saw that our real power P here your P max, here sin delta, and your reactive power it is your, we had the 3, if you will see that is your 3 times Vt upon Xs, Vt upon Xs, here Ef cos delta minus your V terminal. So this delta is the governing criteria for this real power. Why? Because this P max, which is dependent on the terminal voltages, multiplication of the terminal voltage and the excitation voltage, so we have a limitation on this terminal voltage as well as the excitation voltage. Why we have a limitation on the terminal voltage? Due to this again the insulation of this alternator where the bindings are put. So as I said, we can not more than certain terminal voltage. If your insulation is for particular voltage level, then this rating is decided based on that. So if your alternator is rated at 21 kV, then we cannot exceed more than that this voltage. Only we can allow certain percent, that is not more than plus minus 10% in any case. Normally it is not more than plus minus 5%. So we cannot increase this. Similarly here the excitation voltage, this component is nothing but your Vt divided by X3. So you can not increase much, you cannot increase much, you cannot here increase at all, you cannot change. Once the binding is constructed, Xs is fixed. So the only option here, if you want to change the P, you have to go for the delta in change in delta. So we can say this P is directly proportional to delta, because sin delta is a small value, so we can write sin delta as delta. So the real power is mainly governed with your delta, or you can say delta is mainly governed by the real power generation, and the terminal voltage here is controlled by the system. The generation excitation voltage EF is adjusted by generation excited system to control the reactive power. Means to generate this reactive power or to absorb, we can only change this EF, which is in your control. So this Vt is here the system voltage. You have connected this voltage, you may not control. It is very difficult to control this voltage, because this voltage depends upon the system voltage and what is the reactive power injection, etc. But this EF, it is very easily you can control, and that is your excitation voltage. Means excitation, that you can change the excitation, you can, that is a here field voltage basically, nothing else, and by that you can control this. So the reactive power generation and absorption you can control very effectively by changing your EF. So this delta, which controls the real power, means the real power here we can control by changing the delta, and this delta is basically changed by, you cannot change the delta by yourself. Delta can be only changed by the changing the input to the turbine. So this delta is changed by the turbine input power, and therefore we can change the power, and this power changes the frequency of the system. So normally this real power controls the frequency of the system. However, the reactive power, which you can change in the alternators, by changing the excitation, and this reactive power change the voltage of the system. Means how much reactive power you are feeding, and based on that the system voltage profile will be affected. So this real power is directly governed to this, you can say delta change real power, and therefore the frequency, and here your excitation voltage will change your reactive power, and therefore the voltage of the system. So these are basically the couplings. Normally we call the coupled, that is your P delta coupling and the QV coupling, or you can say PV decoupling and Q delta decoupling. So these are the basically used in the load flow analysis and other things. Now let us see again the phasor diagram for the overexcited and underexcited in the different modes. As a synchronous machine, it can run as alternator, it can run as a motor operation. So in the overexcitation mode, here if the current is here lagging, means current is lagging behind this your voltage, terminal voltage, then you can see your excitation voltage EF is more than your VT. So when the current is lagging, and you can say here it is your alternator, this is your reactance and this is your terminal voltage, and here we are talking this current which is going inside this system, that is here system connected. However, this if it is in phase, this current in phase with this voltage, this is called the normal excitation. Means your the phasor sum phasor equation will be, we can write this for the your generator, EF will be your VT plus your IARA plus your J XSIA. Here these are the phasor quantities. So now we have written the phasor diagram, this VT plus IARA, and here with the J sign, here this is added, so this will be your EF. In under excitation, this current leads the voltage, that is a terminal voltage of alternator. Then here it will be addition here, and you can see it may be less than your terminal voltage of this EF. So this is your under excited operation of generator. In other words, here in the motor operation, just it is reverse. Means if your current is lagging, then it is called under excited. If your current is leading, then it is called over excited. Why? Because this is your motor, this is your this, and then this current is coming out from the system. Here it was injecting, here it was coming out. So this sign is changed. So here in the under excitation, if it is lagging, then it will be under excited. However, it is lagging, here it is over excited because it is injecting. And this similarly we can say if it is in the phase with the terminal voltage, then it will be normal excited, and if it is a leading, then it is called over excited of the operation. This is a motor operation, here it is a your generator operation. Now let us see, till now just I discussed about the cylindrical rotor machine. We saw this over excited and the under excited for the motor as well as generator operation. Now this is a diagram of Salient pole synchronous generator. This is your, I can say it is a stator. Here this is your stator, this is the rotor, and it is a Salient, some sort of Salient, because here it is not. In the wound rotor, what will happen? This is your stator, where we will have the binding. So here it is binding, will be, it is cuts, is rotor slots basically, and here we have the 3 bindings, and your this rotor will be here circular. So this is your cylindrical, this is your Salient pole type, because the poles you can see this is Salient, it is outside. The major difference here that in terms of reactances, because this is a circular, so the air gap here between the rotor and the stator is almost constant through the air. Here you can see this is very small here gap, so this is constant. So what is happening that we are going to have excess. Here is a fix, and it can again this is a pole basically, is a field winding where we can have a formation here N and S. Again that can be obtained by the having the winding on the rotor. So here you can say this air gap is uniform, so that's why the reactance between the stator and your rotor is the constant. But here in the Salient you can say the air gap here it is more up to this value, and here it is very small. So in the d axis, it is called the pole. This is your, if it is your north pole, this is south pole, then this is called the field axis, and the d axis is said that the north pole to this stator, and this distance is very small. What does it mean? If this distance is small, means your this L corresponding to this axis will be more, or we can say it is, we know this L is n square upon r. R is the reluctance, and that reluctance here if air gap is less, means reluctance will be less. So what is happening, this xd here is, in this case, is xd is more than your xq, means reactance to the quadrilateral axis where air gap is more. But in this case, whether it is x axis or d axis, it is the same. That is your, this is your cylindrical synchronous generator. Since we have the different reactances along d axis and q axis, then we can have the phasor diagram, and then we can have a current in terms of d axis and q axis current, and we can draw the phasor diagram. So let's suppose this is your terminal voltage, this is your current which is lagging with the power factor angle theta, this is your terminal voltage. Then this current can be decomposed into two components. One is your d axis component, another is your q axis. So this is your d axis current, this is your q axis, and then we can add together. Here resistances are neglected, so we can have here this current id multiplied by xd will be the here, and then it will be this one. So what is happening, we can write the here for this generator E will be, that is EF will be your Vt terminal voltage, plus I can write JXDID plus your JXQ IQ. Means we are here adding some, this basically what is happening here, this is your, if we see the equivalent impedance of XD and XQ, we can have Vt plus some addition this term here we are adding. So this is your equivalent diagram of, this is not equivalent diagram, sorry, it is a phasor diagram of the salient pole synchronous generator. And this generator is used in the hydro generators, because we can go for the, it is only two pole machine, we can go for the several pole machines, and then speed will be changed accordingly. We know this speed that is in RPM, it is 120 F upon P, where P is the number of poles. Now in the previous section we saw that this here real and reactive powers, this real and reactive power, it is only a term of Xs that is appearing. But now we have the two reactances, that is Xd and Xq, and then we can have the expression, and we can derive in the similar fashion, and we can find the real power P for this generator. This is your generator. Here we have a reactance, and this is your terminal voltage. So here we are having the two reactances, that is your Xd and Xq. So the real power is 3 times VTEF upon Xd, and we are having another term here. That term is your 3 times Vt square Xd minus Xq divided by 2 Xd Xq sine 2 delta. Now from this expression you can see we got the similar type of expression here in the your cylindrical rotor. Means your Xd, if your Xd is equal to your Xs and that is equal to your Xq, what will happen? This term is now Xx, and here Xd minus again Xd, if it is equal, then this term will be 0 and this component will vanish. But in this case it is not equal, this will be the different than this, so we are getting another component, and now you can see this component is 2 delta here, sine 2 delta, here is a delta. Means if we draw here this diagram, means earlier we had our P angle, this is for your delta, this is your pi by 2, this is a pi, for this 2 delta. Means here your pi by 2 means here pi it will be your 0. Means here at the pi by 4, what will happen? At the pi by 4 delta, this component will have the maximum value. So what we are going to get? We are going to get another component like this here. So this component, I can say component number 1 and component number 2. So this gives diagram for the component number 2, and this is for your component number 1. So the resultant here, if we want to draw, then we can have here, this will be now added, and this is your shifted slightly, and then we are going to have here slightly this one. So this angle is slightly shifted. This is not pi by 2, it is less than that pi by 2. So this is the real power of our salient power machine. So if you can keep anyhow this is very close to this, then this power we can have the perfect sinusoidal here. The power sinusoidal means the power here P, and here this we are drawing this angle delta, that is your load angle. So this is the term, this is you can say generalized. We can, from this expression we can generalize the wound rotor by putting xc is equal to xs is equal to xq, and then this term will be minus. So it has the double frequency than this first component, and your resultant will be added together and it will be tilted. So this is your real power. Similarly, for your reactive power, you can see now we had this component earlier as well in the cylindrical rotor, but now we are going to get another component. Here this again it is a delta, but we are getting sine square term. So the reactive power here it is added together, and now you can see this is xq minus xd, means here this xq is less than xd. These are the positive quantity. So this xq is now going to be reduced. Here this P is going to be increased slightly in this zone. Up to here it is increasing, and here it is decreasing, means this is your pi by 4. So this value means here if you draw the resultant here, it is slightly, I think it will be here maximum, and here it will be 0 somewhere early. So we cannot go for, even though pi was here, pi is equal to delta is equal to pi. In this case it is less than that. But till delta pi by 4, this P is increased due to this component. But here reactive power, you can see this component is the negative, because this xq is always less than or equal to your xd. So it is basically a reducing term. Here this is always positive, this is positive, this is positive, terminal voltage is possible, and then we are going to have this. In this case also, if any, we can put this xd is equal to x cube, then it is nothing but this component, this whole expression is comes to be this first term only, and this is vanishes out. Means we are getting again wound rotor where xd is equal to x cube. So this is your the real and the reactive power expression, and that can be derived similarly to this wound rotor machine and without any general loss of generality. So we have seen that modeling of in terms of your synchronous generator as well as the synchronous generator of two types, that is the wound rotor and the salient pole machines, and we saw this limitations. First limitations arise in terms of voltage limit, and this voltage limits here I can say this voltage limit is basically of the two regions. First one is due to the dielectric, means the dielectric that we are using, this insulator dielectric, and another due to the heating. So we cannot increase the voltage excessively, that the dielectric material which is there may not sustain, and also it may not be economical. Also due to the heating, suppose here we have the slot where we are just putting the binding. Here we are putting the bindings, various different conductors are there here placed in this. So what happens at these corners, we have the excessive field, and therefore more eddy current that is flowing in this core. This is basically your rotor and stator as well. So what happens here, there is more eddy current and the more loss. So if you are going for more voltage, the more flux and more here stress will be there, and there may be heating, and that is not desirable. So the maximum continuous limit due to the excess flux is lower than that breakdown consideration. Therefore, the limit due to the excess flux is the determining limit. The flux in it that's affected by frequency, that is a core flux, is proportional to the voltage and frequency. So this core heating means we have the two type of heating, but this voltage limit that we cannot go for higher voltage. The heating here we are discussing, this is due to the flux, or you can say the core heating, that is due to the core loss. Means we have the two loss, one is your copper loss, that is I square R loss, and another is your core loss. This core loss, we know it depends on the voltage, that is here is related to your voltage. So no doubt if you can raise the voltage, this current will be reduced, but this loss will be reduced, but this loss will be increased. So we have to see that how much loss, how we are going to heat the core of this here insulating material, and how we are going to dissipate the heat which is generated in terms of core loss. So the voltage limit of the alternator is due to the dielectric, that we should have a cheap dielectric material that can sustain these windings, and there should not be any fault from this here its core, that is outside yoke. And here the heating due to the excessive flux, that is at the sharp edges especially, it is very high, and therefore more eddy current, and there will be more heat, and there may be some hot spot, and there is a possibility that this insulation will get damaged, and that therefore there will be a fault. It is a short circuit fault, line to ground fault, and that we don't want. So this is your voltage limit. Another limit is basically that is called the capability limit of alternator, and that depends upon the various heatings inside, and due to that your I square R heating. So we have the field binding, so we can have the field heating, and we have your armature binding, and then we can have the armature heating. Another is called end zone, means due to this corner and surface, another limit is your that heating limit. So we should, with these heating limits, our generator should operate in those boundaries, that we should not go far more than its allowable permission heating limit. Basically this heating again depends upon how you are going to cool. Means if your cooling system is very, very strong, we must always know why this heating is very important. Suppose here this wire is going on here, and there is some current flowing I. Means here this loss of this bind, if R is a resistance, then loss will be your I square R, and this power is converted in terms of heat. So if you are just heat which is dissipated from this conductor, continuously we are dissipating heat, so the temperature of this body is maintained at particular temperature. But if this heat is not dissipated, means heat generated is not taken away, then the temperature will keep on rise, and that may lead to your here this excessive temperature of the wire may lead to several problems. So this is true for any material, means whatever the heat is generated here, if it is transmitted outside, then we can say we can maintain the temperature. So it is basically the heat which is generated in terms of due to the loss, if we can take it out properly, means there will be no increase in the temperature, and therefore we can operate successfully. So it has some temperature limit. This generator cannot operate more than certain prescribed temperature, otherwise there will be the insulators here, insulations etc. will get damaged. So we must provide the better cooling, so that whatever the loss is going to occur in terms of here in the generator, that must be taken. So that's why for high rating power generators, where there will be more loss, we go for the very better and better cooling, that is we go for the hydrogen cooling. we can go for the water cooling. Various type of cooling scheme, and again the performance depends upon that. Means if your generator is rated at 200 megawatt, and if your hydrogen pressure is reduced, then you cannot operate even though this generator at 200 megawatt. Why? Because the loss which is occurring, it is not dissipated, it is not taken out from that, you can say, the air gap of this alternator. So we have to operate at a lower speed, lower power. So if your alternator cooling is not so strong, then you cannot operate at its rating. So normally in the power generator, power plants, if due to some reason, if the hydrogen pressure is reduced, then generator is reduced, means its capacity is reduced, and at reduced rate it is normally generate the power. So the cooling is very important, but still the cooling, once it is decided, then we should operate this generator its capability limit. So the various type of capability limits, that is your field as well as your armature and your end field heating limits, which I will discuss in the next lecture, and then we will form one zone, and then we will see this is your basically operating, where this is also known as the capability curve in terms of real and reactive power. We will see how this in terms of real and reactive we can draw one zone, and that zone is basically the operating zone, and we also call it the capability curve of synchronous alternator, which we will see in the next lecture. So to recap here, we have seen the limit, the two limits we have seen, that is your voltage limit, and we have also seen that steady state limit of the alternators. We saw the two type of alternators. One is your synchronous wound rotor, another is your salient. Salient generator pole type of generators are used for the hydropower generators, where we generate these we rotate these generators at the lower speed, because the hydro turbines are efficient at the low speed, whereas in the turbo, that is a thermal power station, we operate these alternators at very high, that is maximum speed, so that we can achieve the higher efficiency. And those turbines and thermal power stations, they are more efficient at the higher speed. So we keep the pole as minimum as possible, that is 2 in number, and then speed we achieve, that is a 3000 RPM for 50 Hertz. So this is the basic reason that the thermal power stations alternators, they operate high speed, however the hydro, they operate at less speed. Again, in hydro, the speed keep on changing. In all thermal power stations, the speed is same, that is 3000 RPM. But in hydro, it depends again that how much energy do you have, how much heads you are that is having, that is water head, so that you can discharge that energy. So for hydropower stations, the number of poles are varying from station to station, means the speed of rotation of turbine is also keep on changing. So in next lecture, we will see the various limits, that is the field heating limits, armature heating limits, end heating limits, and then we will derive the capability curve of alternator, and then we will also see the capability of the transmission line and the transformers as well. Thank you.